I'd like to start off today by not talking about science, but by talking about baseball, because we're in the home of the Houston Astros, the 2017 World Series champions. And so I'd like to use the strike zone in baseball as a kind of metaphor for the habitable zone. And so you can envision that planet formation places a planet somewhere near the strike zone or in the strike zone, and life is a batter that is trying to seed life on this planet. And right, if planet formation gives you a planet that has too much incident stellar flux, or is too high, it's thrown with too much energy, it's too hot to be within the habitable zone. It's past the inner edge of the habitable zone. If the picture or planet formation gives you a planet that's receiving too little flux, it's past the outer edge of the habitable zone. And so then it won't be habitable because it's too cold. But you can also envision that maybe the pitcher throws the ball with some spin. So the ball is left or right, and has the planet has the wrong planetary parameters to be habitable. And so it's not just incident stellar flux that controls the habitable zone. Also, the properties of planets themselves control whether or not they could be habitable, whether or not they could have liquid water on their surfaces. And so I'd like to argue that in this talk today. But note that changing planetary parameters doesn't just have some fixed width, it also changes the height of the habitable zone. So just like different hitters have different strike zone heights, right? Changing the planetary parameter will change the width of the habitable zone. And I'll show you that in a bit later. But the point, the main takeaway from this introduction is, right, the habitable zone is a multi-dimensional phase space. It's not just incident stellar flux. It's a variety of planetary parameters that matter and determine the habitable zone. And so the maybe best case for how planetary parameters control the habitable zone is through rotation rate. And so this has been shown in a variety of general circulation modeling work in the past. So here I'm showing you the surface temperature from a simulation of a planet around a sun-like star with an Earth-like rotation rate and Earth-like incident stellar flux, and a simulation of a planet orbiting an M-dwarf star that is tidally locked. So it's receiving all of its flux in the day side, and the substellar point is in the middle of the plot right here. And so you can see, right, that the temperature pattern on these planets is very, very different. So for the Earth-like planet, you have basically a smooth temperature pattern as a function of longitude because it's receiving flux at all longitudes. And you can also see that the temperature pattern is relatively banded because rotation is important in the atmospheric circulation. Whereas for the M-dwarf star, it's rotating extremely slowly. You can see that the rotation period is about 60 days in this model. And so as a result, rotation doesn't influence the circulation at all, and you just have a very hot day side and a very cold night side. And if we look at the cloud fraction from these models, you can see that for the Earth-like model, there's kind of a banded cloud distribution with a lot of clouds at the equator and fewer clouds at mid-latitudes. Whereas for the M-star planet, there's a lot of clouds surrounding the entire day side of the planet. And so there's a really, really high day side cloud fraction for these M-star models. And as a result, right, there's a high day side albedo of the planet, and so the planets can reflect a lot more incident stellar light, and this extends the habitable zone. And so this was shown by Jun Yang a few years ago. So here I'm showing you a classic picture of the habitable zone. So the y-axis is the temperature of the star, up is going to hotter stars, and the x-axis is stellar flux, so going to the left is going to higher incident stellar fluxes. And Jun plotted a few different calculations for the habitable zone from 1D models, which are the solid lines, and 3D models, which are the dashed lines. And you can see that the 3D model predictions for the habitable zone depend really sensitively on the rotation rate. And so the red line here is for slowly rotating planets, and the black line is for rapidly rotating planets. And you can see that the red line extends much, much further in, by about 50% in many cases than the black line. And so this is an example of how the width of the habitable zone may change as you change planetary parameters. So if the planet is rotating more slowly, the width of the habitable zone is larger because the inner edge is closer in to the host star. And so this has been shown, this was talked about yesterday as kind of like an analogy of taking Venus and applying it towards exoplanets, because this may also have applied to Venus in its distant past. And so today I'll be telling you about a suite of general circulation model simulations kind of building off this work using ExoCam. And so I'm using the same model setup as from the GCMs I just showed you. So I'm assuming that there's an aqua planet, I'm assuming only a nitrogen atmosphere, and I'm allowing sea ice to form on the ocean, and there's no added greenhouse gases. And so I'm varying a wide swath of parameters for planets orbiting both sun-like and M-dwarf stars. I'm varying the flux, the rotation period, the radius, the gravity, the surface pressure, and the liquid cloud particle size. But today I'm just going to tell you about the rotation period in the interest of time, also because it is the planetary parameter that affects the climate the most, I would say. The liquid cloud particle size does have a large effect on climate because if you have larger particles, the planets receive more incident stellar flux, but I won't be talking about that today. And so I run simulations for varying rotation period for planets orbiting both Sun-like and M-dwarf stars. And when the planets are orbiting an M-dwarf star, I'm assuming that the planets are tidally locked. So again, the planet's only receiving flux on the day side of the planet. And so these are results for the surface temperature for planets orbiting M-dwarf stars. So again, these are tidally locked planets where the center of each map is the substellar point. And you can see that as I increase the rotation period from a half a day to 16 days, the circulation goes from being very strongly banded at half a day, where the Coriolis force is strongly influencing the circulation, to having a large day-side and night-side temperature contrast, with the day side being very, very hot and the night side being very, very cold. And so in this case, the Coriolis force no longer matters. And so this is a transition between the rapidly rotating and the slowly rotating regimes that was described by Hochmeister et al. And so if we look at the resulting cloud distribution from these models, you can see that the clouds are also very strongly banded at half a day, and then they become very not banded at 16 days, where the clouds are simply high on the day side and low on the night side. And if you look, you can see that there's a really clear transition in the day side cloud distribution between 8 and 16 days, between low day side cloud coverage when the rotation period is 8 days to high day side cloud coverage when the rotation period is 16 days. And so this transition basically shows you when the albedo of the day side becomes large enough to push the inner edge of the habitable zone inwards. Note, I'm not actually changing the incident stellar flux in these models, so I'm just varying one parameter at a time to isolate the effective rotation period on cloud coverage. Okay, and next I'm going to tell you about the results from Sun-like stars. But first, I just want to show you that you can vary the incident stellar flux and the rotation rate consistently. So here I'm showing you on the left-hand panel with a rotation period of 4.11 days with the planet receiving 1 Earth flux. And on the right, this is for a rotation period of 5.5 days with a planet receiving a little bit less flux than Earth. And you can see that, again, on the left-hand panel, we have little cloud on the day side for a fast rotation period. And then we see this transition again to having high cloud on the day side for a little bit slower rotation period. And so you can see this transition happens not just when varying the rotation period alone, but when consistently varying the rotation period and the incident stellar flux. Okay, so now I'll move on to planets around Sun-like stars. And so for planets around Sun-like stars, right, we're no longer tidally locked, and we're just varying the rotation period alone, and the planet's receiving flux, and we're assuming that it has zero obliquity in its incident stellar flux. And so here I'm showing you how the zonal mean zonal wind speed and the stream function vary as a function of rotation period. So these are plots in terms of pressure and latitude space, and they're zonally averaged. And so the colors are showing you the zonal mean, the east-west average of the east-west wind, and the contours are showing you the stream function. And so solid stream functions mean clockwise rotation, and dashed lines mean counterclockwise rotation. And so if you imagine a parcel that is left here at the equator and left to go up, it will go up and then down following these stream functions, and then on the southern hemisphere, up and then down following the stream function. And you can see that as we increase the rotation period in the simulations, the stream function width increases. So this is basically the Hadley cell width is increasing with increasing rotation period. And this has been shown before by Caspian, Schoeman, and many other authors. And you can also see that the flanks of the zonal mean jets that form at the flanks of the stream function increase in latitudinal extent with increasing rotation period. And if we zoom in at two specific simulations to see this more clearly, you can see that with increasing rotation period, the Hadley cell is migrating poleward. That is, the flanks of the Hadley cell are migrating poleward, along with the jets that form at the flanks of the Hadley cell. And also the Hadley cell itself is strengthening. And so the peak in the mass stream function increases with increasing rotation period. And so I wanted to compare these results to simplified simulations that have been done previously to see if our results using this more complicated GCM that includes sea ice formation and more detailed radiative transfer agree with simpler simulations. And so here I'm comparing the results to an idealized general circulation model that's double gray and has no clouds, and this is from Caspian, Schoeman 2015. And here I'm plotting the latitude of the maximum wind speed, basically the extent of the Hadley cell, as a function of rotation rate. And you can see that between this work and the more idealized general circulation model, the Hadley cell extent agrees very, very well, has a similar width in both models, and the Hadley cell decreases in extent with increasing rotation rate. However, the equator to pole temperature differences in the models are very, very different. We found a much, much larger equator to pole temperature difference by up to 100 Kelvin. And the reason is that we're including sea ice in our model. And also, Caspian and Showman tune their model to reproduce Earth-like conditions for Earth-like parameters, whereas we're not tuning our model and we're not adding greenhouse gases to increase the temperature and reduce sea ice formation. However, you can see that both models do predict that the equator pole temperature difference should increase with increasing rotation rate, just because it's harder for eddies to transport heat to the pole with increasing rotation rate. And so I'd like to just conclude by reminding everybody that the habitable zone is a multi-dimensional phase space. And if you like baseball, you can use the strike zone as a nice analogy for the habitable zone. Planets orbiting M-dwarfs have a cloud transition between 8 and 16 days, assuming that the flux isn't changing. It could be at higher or lower rotation period for different stellar types. But regardless, there's a transition depending on the rotation rate, between which one has low dayside cloud coverage and high dayside cloud coverage with increasing rotation period. And for planets orbiting sun-like stars, slower rotating planets have wider and more vigorous Hadley cells. And so I'll just leave these conclusions up and take any questions. Thank you.
The last plot of results you showed of equator to pole temperature contrast versus rotation rate. If you can go back, it seemed like your results aren't quite monotonic. Is that a real effect? There's kind of a the first 2 points go up and then there's a drop. What's that all about?
Yeah, so it's a real effect. I think it's happening. So basically, you start to have a ferrule cell appearing in the model, and so I think it's kind of like an effect where the eddies start to matter, and basically you no longer have purely barotropic heat transport, and where you start getting baroclinic effects, there's a little drop in our model. And you can also see it's kind of not exactly monotonic in the Caspian Showman results either. So it has to do with the mid-latitude baroclinic effects. Yeah.
Perhaps I missed this, but what's the ocean doing in these simulations? Ocean dynamics?
Nothing, just a Q flux. Yeah, I didn't say that.
What changes would you expect if you put in a fully dynamic ocean?
Yeah, I would expect it to greatly increase the equator to pole heat transport, for example. And yeah, as June showed, it would also change the dynamics of the actual like surface temperature distribution, right? You would have a kind of more like sheared out lobster-like substellar point temperature pattern than having just the pure dayside, hot dayside, cold nightside pattern that we see in our simulations.
Yeah, so that's good. Yeah, that's exactly part of my question that Robin just mentioned, that part of all these simulations in the past for the inner edge showing that rotation rate has this really huge effect on the inner edge is because they're all partly because they're using slab ocean GCMs. So, if you go to, I would suspect if you go to a more, use the dynamic ocean, have a dynamic transport, then that would modulate, the temperature differences a bit more. The other thing is, the Yang 2014, even in the subsequent slab ocean GCM simulations, they've been showing a progressive movement. The inner edge has been moving actually farther out with improved convection schemes and rate of transfer. There were also some issues with the orbital calculations and whatnot. So, I think the latest results been et al. 2018, earlier this year, I think, came up with something that was considerably, more like the 1D results than the Yang results. So, it's changed a lot.
So I think I agree that the details do matter depending on your convection schemes and the exact GCM you use. But the idea that you have a transition in the dayside cloud coverage, I think, is pretty robust. Mike Way just wrote a paper using Rocky 3D where he shows that it is pretty robust, and he actually changed the actual convective parameterizations and showed that even changing the convective parameterizations over a wide swath within his model, he found that the dayside cloud distribution, the idea that there is a transition where you get large dayside cloud, is pretty robust, and that seems to be robust through a variety of general circulation models.
You still get the dayside clouds, but the issues with the heat transport, how vigorous that is, and that seems to vary.
Yeah, I agree that the details vary between models and depends what physics you put in. Yep.
Oh, thank you. For your M-dwarf cloud coverage plot, in addition to the inner edge of the habitable zone from the temperature-dependent habitable zone, you also have the inner edge of the stellar activity habitable zone. And it struck me, maybe you could use these larger cloud coverage fractions in the habitable regions of the planets to maybe extend the inner edge of the stellar activity habitable zone too. Do you have any future work passing stellar activity through your GCM model?
Oh, I haven't thought about that, but that sounds really interesting. So is your idea that stellar activity, like the cloud coverage would somehow protect you from stellar activity?
Absolutely. It'd be a great UV cover.
Oh, that's really interesting. Yeah, thanks.